me, first I want to show you a picture of what the problem is. No water. And at first sight, to me at least, from where I live, this seems to be not understandable, because Brazil is one of the countries that gets most rainfall. So why is this? And one thing I want to say that I don't think has been said, but that should be said, São Paulo has grown unsustainably large. So this is, I looked up the population size of São Paulo. That's only the city itself, not all the cities around it. In 1940, there was only a little over 1 million people living here. 2010, more than 10 times as big. And these are two satellite pictures, one from 1986 and one from 2013. So you can really see how São Paulo has spread even in these 20 years. And this would not be such a problem if there was a huge river network feeding São Paulo. But this is obviously in South America. And I've overlaid the natural watersheds, and well, here, and the watersheds that are very much richer, as was pointed out here in the Amazon basin. But the fact is that no big rivers drain this way. And then if one overlays a drought risk map, well, the drought risk is actually not that severe around here. It's much more severe here, but it's magnified by the population. So if you just plot for the different states of Brazil the water resources per person, then you see that we're looking really bad here and really good up there. So I think this is just pointed out the network of reservoirs, and this is a picture that I took of Wikipedia, where you can see how the reservoirs have been declining even with the introduction of deeper pipes that is not long-term sustainable. So this is sort of my introduction. I want to talk about long-term problems with water that have to do with global warming. And so let's start with the atmosphere. The atmosphere, this is the composition. It's 78% nitrogen, 21% oxygen, 1% argon, and 400 ppm carbon dioxide. So 2 years ago, we first crossed this 400 ppm threshold, and next year we will never go below it again. The total mass of the atmosphere is 5 times 10 to the 18 kilograms, and each one of those 1 ppm of carbon dioxide weighs 8 billion tons. So historically, this is a picture from our textbook. These are the last 500,000 years or so. Historically, the carbon dioxide level in the atmosphere has fluctuated between a low of about 190 parts per million and up to 300. And then when you magnify in the last 1,000 years, this sometimes is called the hockey stick. Hockey is not a very popular sport in Brazil, but it's played by people running on skates or on ice, and they have sticks in their hands and they have bends in the bottom like this. So this is called the hockey stick graph because it's horizontal for the better part of the last 1,000 years. And then with the beginning of the Industrial Revolution, this has shot up like this. And if we're just magnifying the last 1,000 or 15 years, there's two sets of measurements that I list here. One is the air over the South Pole, and then this is the air in Hawaii. And what you can see is that there are annual fluctuations up and down. And in Hawaii, they correspond to about 7 parts per million, which is plants growing and absorbing carbon dioxide, and then in the winter dying and releasing the carbon dioxide. And you can see that in the northern and the southern hemisphere, because of these wind currents that were just mentioned, the northern and the southern hemisphere don't mix a lot. And so carbon dioxide, by and large, is not transported across in large enough quantities to counteract the seasonal effects. Of course, when it's winter here, it's summer in the northern hemisphere, and that's why these two oscillations are opposite in direction. And most of the plant mass is in the northern hemisphere, and that's why the northern hemisphere oscillations are big. The biggest problem in this graph is not these oscillations, their nature, and it's good that they're there, but that you have a steady rise of about 2 parts per million, which means 16 billion tons of carbon dioxide get added every year to the atmosphere. And with it, the global temperature is rising. And so when we talk about the global temperature, obviously you have to average over the entire year, but also over the entire globe. And then different averaging procedures have been applied, sometimes necessitated by measurement stations not having been in place for a long time. Sometimes necessitated by different considerations. For example, you can weigh the land area different than the sea area. So this, by the way, is a satellite picture from June 1992 of the global average temperature, that 1 month. What you can see is when you do the averaging over the entire globe, in any given year, there is a tendency that has been going on for the last century where this temperature slowly rises. Currently, the best estimate is about 0.2 of a degree Celsius per decade. For a few years, it seemed like this tendency had saturated that year, but this is not on this plot. The last year was the hottest on record. Now, the effect of a higher temperature is that more water can be in the atmosphere. So this would actually be good for drought prevention, right? So what I plot here is, well, first of all, the current average of water content in the atmosphere is 1/4 of 1%, worldwide average. I just said that the atmosphere weighs 5 times 10 to the 18 kilograms, so this is roughly 10 to the 16 kilograms of water that are in the air at any given time. If the temperature of the globe rises, that means that the atmosphere can hold more water and there's more precipitation on average. I showed this here where I plot the dew point temperature as a function of the air temperature and as a function of the relative humidity. And basically, any point under this tent is a possible condition of the atmosphere. So obviously, if you raise the temperature, then make the tent higher, you can store more water in the atmosphere. This is an interesting satellite movie from NASA's Earth Observatory, and what I will show here is starting in July 2002, month by month until now. On this side, what the amount of water vapor is in the air, and what the total rainfall is. So here, the yellow means very little water vapor, as was just pointed out in the Sahara. There's almost no moisture, and blue means high water vapor content, like here over the Amazonian. And then this is the measure for the rainfall. This was also just pointed out, very dry here and here, from almost no rainfall to 2,000 millimeters. And just to give us a scale, the equivalent water depth of our atmosphere is 10 meters. So 0.25% water in the atmosphere means about an average of 2.5 centimeter water vapor column. This goes from 0 to 6, that sets the scale. As far as the rainfall is concerned, the rule of thumb that I always use is that the global annual precipitation, rain and snow, add up to about 1 meter, about this high. 1 meter is 1,000 millimeters, so this is 1,000 liters per square meter. 1,000 millimeter, well, this logarithmic scale is about here. Okay, so what I find more interesting to plot is the annual snowfall. And so what I've done here is map. I also use these Earth observatory data projected obscurity in 3 different views. This is North America centered, this is South America centered, and this is Eurasia centered. And these are the actual colors of the Earth, not some kind of enhanced, but to the clouds subtracted. So this Earth observatory satellite goes over and over, and they just take picture after picture. When they have a non-cloudy picture, then they use that. And so this is the superposition of all of them for the entire year 2013. So when I start this January, February, March, and so on, this will go around here. And what you will see is in January is our winter in North America. This is where I live. Basically, my entire state is covered with snow for the entire month of January. In Canada, of course, the entire country of Canada is covered. Down here, there's almost no snow in January. Russia is covered by snow. So I let this run. And so you can see that the snow retreats in the northern hemisphere summer months, August and so on, and then goes down again. And it should have looped, but it does not. Here in South America, you can see that when Europe winter months roll around, the Andes get snow covered. But this is actually a unique effect that we had last year. And so let me show you how this looked since 2000. So this is the snow cover in this worldwide projection. And here's the fraction of snow cover for each of these pixels. So this goes a lot faster, tenths of a second per month, because otherwise they have to wait so long. For 2002, it will loop all the way to 2015. You can see how the northern hemisphere gets covered again and again. There are uncovered parts. This is an artifact because of satellite coverage. And down here you can see the snow cover in the Andes very. So this angle up and down of the snow cover in the northern hemisphere is really, really important for the overall albedo of the planet, the amount of sun that the planet can reflect. If this snow cover gets reduced significantly a few years in a row, then it becomes a self-accelerating aspect. The previous speaker just talked about the radiation balance of the atmosphere, and that is drastically changed if there's snow on the ground and no snow on the ground. But for the purpose of this region, I tried to concentrate on just the August snow cover. So I only looked at the thickest of the winter months and played that movie. So only those slides that are August, I let each one sit there for 2 seconds. And I wanted to see if there is a discernible change in the snow cover in the Andes in the last 15 years. And I have to say the signal is not very clear. It seemed to be a period of enhanced snow cover in 2003 to 2005, but over the last few years it has been roughly the same. I thought I had it in 2013, but apparently not. So this is the land surface temperature anomaly that was previously mentioned compared to the annual snowfall. And again, it's really hard to see any clear signal what's happening. The tendencies in global warming are just, they're there, but very weak over time. After all, the global temperature rise is only 0.2 of a degree per decade. Well, nevertheless, there are big effects. So you're not the only place that has droughts. This is a picture that just was in the Los Angeles Times of one of the reservoirs, the Lake Oroville Reservoir, and you can see that this is normally full, and so they're 50 meters down from their peak level in that reservoir. Perhaps even more impressive is this picture, because this Folsom Lake is also a reservoir. Usually it's used for boating, so these are boat docks, and the lake has receded to a very, very small fraction of what it was, and 600 boat docks are just lying here and cannot be used anymore. So here there is a clear signal relative to the snow cover. So this is a satellite picture of just California. And you see the Central Valley and then the Sierra Nevada mountains, and the rest of the Rockies is further out. And this picture was taken in just this year, 2 months ago, January 2015, and there's a little bit of snow cover here. This is from January 2013, and you can really see the difference. Now, the winter in 2014 was the hottest in the history of California. So last year, the winter temperature across the state was 7.6 degrees Celsius. That's the average in winter, even up on the mountains. This year's winter temperature has gone up another degree. So if you think you're in trouble, they're in much bigger trouble. So these are drought projections projected forward. All these models, of course, are developed by comparing historical data, fine-tuning the parameters, and then calculating forward to see what will happen. And these are two regions, the Southwest, which is this region, and then the Central Plains, which is this region. And basically you see that starting now, they predict bigger and bigger and bigger water deficits in the south and west of the United States. And so these are now likelihood projections that there will be decades of droughts and multi-decade long droughts. And there are three climate models that I show here, red, green, and blue. And so in the Central Plains states, this is the 1950 to 2000 interval, and this is the 2050 to 2100 interval projected forward. And you can see that the probability for a decade-long drought is basically twice as high in the Central Plains, and while there was almost no probability for a multi-decade-long drought period, that seems to be the new norm at the end of the century for the Central Plains. In the Southwest, the same picture. Of course, then what people do is they tap into the groundwater. So this is a picture of the main aquifers in the United States. This aquifer is under the Central Valley in California. And since farmers don't get enough precipitation and not enough allotment from the rivers and the aqueducts, they drill deeper and deeper into the aquifers. This is another interesting one in the Central Plains that's called the Ogallala Aquifer. And the reason why this is so important is because it's used for farming irrigation, but it's also under danger from fracking for natural gas. So this is in the central level, in the Central Valley in California, starting in 1962, the change in the groundwater level. And in blue there are the red periods with high precipitation, and in white the dry ones, low precipitation. That's also due to El Niño and El Niño, as was just pointed out. But you can see that in the dry periods, the groundwater level falls a lot faster than it rises in the wet periods, and so overall the groundwater has fallen and fallen. And actually, this NASA GRACE satellite can make very, very sensitive measurements of the altitude below it. And they have actually found that the Central Valley in California, due to pumping out of the groundwater under it, has fallen in the last decade by 30 centimeters. And of course, in the US, this is probably the main vegetable growing region, the Central Valley in California. So 99% of the artichokes, 99% of the almonds, 98% of the garlic, tomatoes, all the strawberries, all of this comes from this region in the US. So this is a big problem, not just for California, but the US. A different version of this graph was just shown in the previous presentation. It says how far below ground are the groundwater resources that you can tap into with your wells. And obviously here in the Amazon basin, you just basically step really hard on the ground, your feet get wet because the groundwater is right below the soil. Here it's quite a bit different. This scale is 300 meters, this is 600 meters. So you have to drill quite a bit. Okay, I'm pretty much exceeded my time, but I wanted to cover a few other intersection points between water and energy, and they are well, we have renewable fuels that we can make out of plants. So here in Brazil, this is mainly for sugarcane. Professor Goldberg was at some point supposed to be here, but I'm not sure he's still on the program. He and I had this discussion before. You really need water to make this an economically viable proposition. In the US, we don't grow sugarcane, we grow corn to make biofuels, in particular bioethanol, which is not a good end product out of corn. I pointed that out last year here. What makes it worse is, so this is a precipitation map of the United States, and you can see this side of the country is much wetter than this side of the country. And so while it makes sense to grow corn in this area, it really doesn't make sense to grow corn here because you need so much water from artificial irrigation. And this is exactly where the main corn growing states in the US are. So plants need water, and if you want to produce renewable energy out of plants, you have to be careful that you have actually enough natural rainfall, because otherwise you're inducing a very unwanted correlation. Of course, you can also use energy to turn that into water, and that's something that this region may need to consider, and that is desalination. And so I just studied how much energy does it take to take the salt out of salt water. And the best plants to do this are reverse osmosis plants. There's also plants where you heat the water and basically distill it, but that's really only useful in areas where you can then use the warm water to heat your buildings too. And that really doesn't work for it. So for this area, only desalination is a viable technique. And then the most efficient of these plants spend about 5 kilowatt hours per cubic meter of water. So 1,000 liter, and it costs you about 1.5 or 2 reais to make 1,000 liters of water. So that's a very workable proposition from an energy money standpoint. Worldwide, there are more than 15,000 desalination plants, and each, well, I don't know how many overall desalination plants are. I just looked up the numbers for large desalination plants, which make about 1,000 cubic meters per hour or more. And so 15,000 of these are already there. This is an example from Barcelona in Spain, for example. So this is a very workable technology that people may want to consider much more. I already touched on this. So what I'm showing here is hydraulic fracking. What's done there is you drill wells into the ground, 1, 2, 3 kilometers deep, and then you force a mixture of water and some chemicals and also fine sand down these wells to fracture the rock. And then you have other boreholes through which you let whatever you have released down there escape up, and you hope that it's mainly methane. And this works actually amazingly well, and over the last maybe 5 years, in the US, the energy landscape has totally changed. The US is now a net exporter of energy because of the abundant resources of natural gas that have been released through hydraulic fracturing. And so this is an overall picture, county by county, how many wells there are. And, there are about 40,000 or so of these. There are these little black dots that you can see here. And the major areas are this Marcellus and Utica shale here. And then you can see North Dakota and even going into the Plain States, and in particular Texas, all these wells. And what's overlaid then is the water stress that exists in these areas. So low stress are the yellow areas, and then it goes to dark red, where it's extremely high stress. And you can see that a lot of this fracturing, again, is in very high stress water areas, and that is in here too. That's a problem. In the US currently, about 150 billion, so that's 150,000 million liters of water are used for fracking and lost in the process each year. So this is a very large problem, in particular in the West. Here, these areas are the Great Lakes in black, and of course I live here in Michigan, in the middle of these Great Lakes. If we have one thing, we have water. Alright, so water and energy, and this is my summary. There's a strong coupling between the two. So water is needed for energy production in fracking, I just talked about, in biofuels, but also if you want to do burning of fossil fuels and driving a turbine, that also involves heating water and letting the water vapor become steam and driving a turbine. And in most of these power plants, huge amounts of water are needed. Energy can be used to gain water resources, and I haven't talked about this, but simple pumping is a possibility. When people talk about, for example, the Keystone XL pipeline, basically from Canada all the way to the United States into the Gulf of Mexico, and pump huge amounts of oil, that is an economically viable proposition. You can think in the same way about water. And so I just raise this as a question. I'm not sure that I want to recommend this. It's probably a nonsensical idea, but at least somebody should think about it. And desalination, I think, has a lower price point than this idea because it costs energy to move water. Where I spend most of my time on is this indirect coupling between water and energy to global warming. We cause global warming by burning fossil fuels and adding CO2 to the atmosphere, and therefore raising the overall temperature of the atmosphere, which this warming of the Earth then reduces the snowpack, and when the snowpack is reduced, you destroy the ability in many parts of the Earth. I talked about California and the Rockies, but this is an even bigger problem in the Himalayas and the large streams in China and Southeast Asia that are fed by melting water. So when you destroy the snowpack, water emergencies in the regions that depend on that melting water are an unavoidable consequence. So thank you for your attention.